Hello everyone, welcome to our second session on formation of PDE by elimination of arbitrary constants. Things to remember, already we saw what is the PDE, which is nothing but a differential equation involving more than one independent variables and any number of dependent variables is called a PDE. Let us consider a function of x and y as z, then the partial derivatives of z with respect to x and y can be written as dou z by dou x and dou z by dou y. And for this derivatives, we can use the notation as p and q. Similarly, the second order derivatives of z with respect to x and y, that are dou square z by dou x square, can be taken as r, and dou square z by dou y square can be taken as t, and dou square z by dou x dou y can be taken as s. So these are the notations we are going to use to denote these partial derivatives. Now let's come to the formation of PDE. So first we are going to see one example in which we are going to see how to eliminate the arbitrary constants to form a PDE. So the problem is z is equal to x square plus a into y square plus b. As you know, this equation involves two arbitrary constants. So we have to remember here one thing, that if the given equation involves the arbitrary constants that equals the number of independent variables, the resultant PDE will be of first order. So our resultant PDE is going to be the first order partial differential equation. So we are going to differentiate the given equation only once. That is, differentiating z with respect to x partially, we get dou z by dou x. This can be taken as p. So in the right hand side, this is treated as a constant term since it involves y. There is no x here. So differentiating this with respect to x, we get 2x. So we get 2x into y square plus b. Similarly, differentiating one partially with respect to y, we get dou z by dou y, which can be taken as q. And in the right hand side, here the first term is treated as a constant term. So this is a fixed term. Now differentiating the second, you get 2y. So 2y into x square plus a. So from this we get the substitution for y square b as p by 2x, and for x square plus a as q by 2y. So now using these substitutions in 1, we can replace the constants in terms of x and y. So substituting these two in the equation 1, we get in 1, we get our resultant PDE as p by 2x into q by 2y. So, and hence by simplification we get the final form of PDE as 4xyz is equal to p into q. So this is what our resultant PDE. Now let's see another example. Here the problem is we have to form a PDE of all planes cutting equal intercepts from the x and y axis. We know what is the equation of a plane having intercepts as ABC from x, y and z axis. That is x by a plus y by b plus z by c is equal to 1. But here it is mentioned that it has equal intercepts from x and y. So this b also can be taken as a. So the given equation is x by a plus y by a plus z by c is equal to 1. So in the given equation also we have only two arbitrary constants, that are a and c. So the resultant PD is going to be the equation of first order. So now we are going to differentiate this partial with respect to x. This gives us 1 by a plus 1 by c, and differentiating z, it is dou z by dou x, that can be taken as p, And in the right hand side differentiating 1 we get 0. Similarly, differentiating 1 partially with respect to y, first term becomes 0 because there is no y in the first term. So second term becomes 1 by a, plus in the third term it is 1 by c into differentiating z with respect to y partially, it comes as q, and in the right hand side 0. So from this we get 1 by a is equal to minus p by c, and from the second equation we get 1 by a is equal to minus q by c. So now comparing these two, we can write 1 by a is equal to minus p by c as well as equal to minus q by c. So comparing this, we can write minus p by c is equal to minus q by c. This implies that we get P is equal to Q as our resultant PDE. So this is how we are eliminating the arbitrary constants from the given equation to form a PDE. Hope you understood. Thank you.